Hello, everybody. Want to welcome you all to another systems lunch. I'm delighted today to have Emina Torlak visiting from the University of Washington from the comfort of her home. Today, Emina is going to be talking about solver-aided programming for all. Emina is an associate professor at the University of Washington, aka UW. Emina is a programming languages person. I would say I'd like to claim her for programming languages, but she publishes in a wide range of areas. She characterizes it as being at the intersection of formal languages, formal methods. There's also computer verification, computer-aided verification, software engineering, but really touching all sorts of fields and just doing tons of cool stuff. Bringing solvers to everywhere. So I'm really looking forward to her talk. In addition to creating Rosette, which is this now very famous system that Emina has created and spearheaded, she also created this previous system called CodCod, which is a constraint solver that was used also widely. But today's focus is, I believe, going to be entirely on Rosette, also judging from the little picture on the screen. So with that, please take it away, Emina.
Thank you, Emery, for the very kind introduction, and thank you all for joining. It is my pleasure to visit virtually and tell you about solver-aided programming. So what is solver-aided programming? At a high level, it is a programming model that integrates automated theorem provers, specifically SMT solvers, into your programming language, providing constructs for verifying and synthesizing code from within the language. Now, the key here is that a solver-aided programming language allows you to interact with the SMT solver at a very high level. You never have to generate any constraints, and you never have to worry about how to express the semantics of your program as a logical formula. This has enabled a very wide range of programmers, from high school students to undergrads to professional software developers to my favorite audience, grad students, to build state-of-the-art verification and synthesis tools for new domains in a fraction of the time that it would have before taken an expert like me to build one without the help of a solver-aided programming language. So the particular language I'm going to be talking about today, as Emery mentioned, is called Rosette, and it is the one that I have been developing for the past decade or so. So the talk is going to contain three parts. The first thing I'm going to do is I'm going to introduce the notion of a solver-aided tool, just kind of remind you of how it works and what it does and why you might want to have one. Then we'll briefly touch upon why it was really hard to build one in the past, why it took an enormous amount of time and expertise to build them before we had things like Rosette. The next thing I'm going to do is talk about Rosette itself. So what does it do that helps you avoid the hard parts of building these tools? How does it help you? And we're going to do this in two parts. The first thing I'm going to do is I'm going to show you how to use Rosette to build a tiny programming language, and of course, a verifier and a synthesizer for that language. Then I will give you a brief idea of how Rosette works internally. So what is it that enables it to let you build these tools so rapidly. Finally, I will conclude by briefly mentioning some of the recent applications of Rosette. So it has been used pretty widely since it was first released in 2014 in both academia and industry. And the particular tool that I will be talking about today is one that we developed last year, and it was used to verify parts of the Linux kernel. All right, so let's talk about solver-aided tools first. The easiest way to understand what solver-aided programming is by contrast to the thing that you already know, which is classic programming. So classic programming is really an exercise in human compilation, okay? So you as the human being, you as the programmer, have some specification in mind, something that you want the computer to do, and you translate that specification manually into code. Now, the only way that you have in a normal programming language to check that your code meets the specification is through testing. Okay, so we all love testing, we all do it. And in fact, even if you have a verifier in your system, you should test your code. But you test your code So essentially, at a high level, what you're doing every time you're testing your code, you write a unit test, you write some property of your code that you wanted to satisfy. So here in this little mockup, I wrote this property called safe. It takes as input some value and the output of P on that value, and it returns a Boolean flag true if P produced the correct output for that input, otherwise it returns false. And of course, if it returns false, the assertion fails. So this is familiar to everybody. So essentially what testing is doing is picking concrete points in the space of all inputs and checking that your program is doing the right thing on those concrete points. Now, when you bring a solver into this system, into this environment, what it gives you is the ability to ask richer queries. So instead of asking about the behavior of this program P on just one input 2, you can actually ask whether P is correct on all possible inputs. So what we're doing here is essentially the only thing that has changed in this picture is I have replaced that concrete value 2 with this value x. This is a symbolic integer, and you can think of it as a logical variable, like a mathematical variable x that stands for an arbitrary integer. Okay, so once you're able to do this, you can ask the solver questions such as, find me an input on which the program fails. This is the classic verification question. The way that it's answered is by reducing the semantics of this program, its meaning, all possible behaviors, and the semantics of this predicate, of course, to logical constraints. So they look like this. I'm showing them in bold here. So this is the logical encoding of safe and logical encoding of P. And then we wrap that into some quantifiers, okay? So what this formula here is saying is we're asking the solver, does there exist an X such that P is not safe on that input? If it does, then you have found a real bug, a concrete counterexample. And if it doesn't, you know that your program is correct. So in this case, suppose that we have found a bug. So P fails on input 42. The next thing that you would do, of course, is debug and localize your fault. And let's suppose that you localize it to this expression right here, this thing that computes this local variable v. Now, if you don't know how to fix v, how to write the expression correctly, the solver can help you there as well. So you can replace the buggy expression with these double question marks. They stand for a hole in the program. And what happens next is we can issue a synthesis query. So what this is saying is, does there exist an expression E in our programming language such that when we take this E and we plug it into this place where the double question marks are, then P will be correct on all input X. Okay, so this is what this query is saying. So it's another thing where we have had to reduce the semantics of this program with a hole now and the semantics of safe down to constraints, and we wrap it into some quantifiers and we get something useful, right? The solver is synthesizing an expression for us. Now, usually in this part of the talk, somebody asks me, well, why don't you just put double question marks for the entire body of P, right? I mean, that seems like the easy way out. And the answer is you can do that in theory. In practice, of course, it's not going to work. These tools are solving extremely intractable problems. So in practice, depending on your programming language and what you're trying to do, synthesis tools are able to generate on the order of, a few tens of lines of code, essentially the body of a procedure. It's not going to generate a million of lines of Java code for you, for example. Okay, so this is what solver-aided tools are, and I hope you would like to have one for your favorite programming language. And now the question is, well, why doesn't every language have one? And the answer is they're really hard to build. So specifically, what both of these things have in common is this need for a symbolic compiler, something that will take as input a program and generate constraints that encode its meaning, okay? So building compilers is hard, and that's actually what takes most of the time here, or that used to take most of the time here, and requires expertise in programming languages and formal methods and software engineering. And this is not surprising, right? I mean, think about how long it took to build something like GCC, compiling any high-level language down to something very low level, especially something so far from a programming language like first-order logic is very hard. So what really motivated Rosette back when we started working on it was the following question: can we avoid building the compiler? So if you're a programming languages person, you know that there are other ways to run your code, to give meaning to programming languages, and a particularly popular one, of course, is building an interpreter. So That question was, can we just somehow have you provide an interpreter for your source language? Okay, you just write an interpreter, and something takes that interpreter and turns it into a compiler to constraints. And the answer is yes, as long as you build your interpreter in a solver-aided host language, such as Rosette, which runs on top of a non-standard virtual machine. I call it a symbolic virtual machine that will do the translation to constraints for you. So essentially what's happening is you have an interpreter for your language. This is providing the semantics for your language. You have a program running on top of that interpreter. And what Rosette does, it essentially translates the composition of these two functions into constraints. And of course, this is already hard because I told you just writing one compiler is hard. Just translating this one function is hard. And I'm telling you that now we can translate the composition of them efficiently. And that is basically the main technical challenge that the original Rosette paper addressed. And I will show you later in the talk how this is done. I will give you some intuition about how this actually works. Before we do that, though, I'm going to tell you a little bit more about what Rosette is, what it looks like on the surface, and how you use it to build tools. At a high level, when you're using, the process of using Rosette, the process of building tools with Rosette is an exercise in language embedding. Okay, so your source language, the one that you want to analyze, we're going to call it the guest language. And the implementation language is the host language, so the language in which you're going to implement an interpreter for your guest. There are two ways to embed a guest language into a host language. One of them is called the shallow embedding, which means that your guest language is basically an API or a library in the host language, and the syntax of the guest language looks very much like the syntax of the host language. The other approach is, of course, interpretation. This is called deep embedding. And in that case, you're building an interpreter in your host language for the guest language, and guest language can look in any way. It doesn't have to have the same syntax as the host language. So you have seen many examples of these things before, of both guest languages and host languages. And of course, this distinction between a guest and a host is pairwise, right? So there can be a language that's both, and there are many of them that are both a host and a guest language. Okay, but this is the basic setup. In order to build tools in Rosette, you will do language embedding. So how do you embed languages? So we know how to do this in a normal programming language. You've done it before, for sure. So how do we do it in a solver-aided language? Well, it's really the same thing. The only difference is that you're using a solver-aided host language as your implementation language for the source. And of course, Rosette is one such language, and many guest languages have been built in it. And as I said, the one that we're going to see at the end is this language for reasoning about just-in-time compilers for Linux. Okay, so what is Rosette? Well, it is an extension. It is itself a guest language, actually, an existing host language called Racket. And it adds to Racket a couple of key constructs that make it possible to express these verification and synthesis questions about the code that you're writing. So if you're not familiar with Racket, it is a modern descendant of Scheme and Lisp. So, you know, there are a lot of parentheses, but I don't know, I got used to them. I really kind of like them. And it has, the main feature is that it has powerful metaprogramming facilities, which made it possible for me to build Rosette. And of course, which make it possible for you as the user of Rosette to build new languages on top of it. The constructs that Rosette adds to Racket look like this. I'm not going to drag you through these in details right now. I will actually show you how to use them and what they mean. But essentially, there are three kinds of constructs that you add to a host language to make it a solver-aided host. You need to have some way to introduce symbolic values into your program. So if you remember that cartoon and the variable x, so this is essentially how you introduced a symbolic value of a given type into a Rosette program. Of course, you need to be able to express properties of your program. So these are your assertions. And then you have to be able to ask queries about program behavior. And this is what the verify and synthesis query are doing. All right. So let's see how all of this works on a concrete example. So what we're going to do here is we are going to implement a tiny solver-aided guest language that is essentially, think about it as arithmetic only subset of something very low level, some sort of a low level assembly where we can do addition, subtraction, bitwise operations, you know, the usual thing on 32-bit integers. Okay, so of course what we want to do is we want to be able to test and run the programs in our BV language. One advantage of building tools using Rosette by building an interpreter is that you can actually do differential testing. So you can check that your model of the semantics, which is your Rosette interpreter, is actually correct with respect to the real thing. So for example, if you were writing an interpreter for RISC-V in Rosette, which is something that we have done, you can test it against an existing reference simulator for RISC-V to make sure that you got the semantics correct. So that's one nice thing about being able to run your code and not just think about it statically, analyze it statically. So in addition to running and testing these programs, you want to be able to verify them, of course, that's the whole point of the exercise, and to synthesize them. Here's how we're going to proceed. 3 steps. The first one is we're going to write an interpreter. That's 50 lines of code. I'm going to show you 10 of those. The remaining 40 are just helper functions that make the 10 that I'm going to show you look nice. That's basically what it is. Then we're going to see how to write the verifier and how to write the synthesizer for almost free. So an additional 5 to 15 lines of code. All right, so I'm going to show you how this interpreter works by walking you through its operation on a tiny example. So this BVMax function is a function in our guest language. It takes as input 2 32-bit integers and calculates their max without doing any branching. And we would like to execute this on 2 super simple inputs, -1, -2. The first thing that happens is, of course, we have to parse this into something that has more parentheses, okay? So here is a very simple representation of this AST. It is a list of lists. So the entire program is a list, and each innermost list represents an instruction. And they are structured as follows. The first value in the list is the identifier of the output register. So this is where the instruction is going to write its value. The second value is a symbol. It is the opcode, so the instruction you want to execute. And the remaining values are the identifiers of the input registers or the immediate constants, but we're not going to worry about that. Okay, so you can think of it as just the identifiers for the input registers. The next thing that happens is we're going to interpret the program. So we're going to pass the program, the AST, to the interpreter and the 2 inputs. And the first thing that's going to happen is that this make registers helper function is going to create enough registers to execute the program. In this simple language, you can tell exactly how many you need. It's just the length of the program plus the number of inputs, and it's going to populate the first n slots in this little register array with the 2 inputs to the program. The next thing that's going to happen is we're going to enter this interpretation loop, and we're going to use Racket's pattern matching to bind the local variables out, opcode, and in to the parts of the corresponding parts of the instruction. Okay, so the output register, the opcode, and in is now bound to a list of the input registers. The next thing that's going to happen is we're going to run this lookup function, which is just really doing a lookup in a giant table, and it's going to turn this opcode. It's going to return the lambda, the actual procedure, the implementation that provides the meaning, the semantics of this opcode. Then we are going to load the values of the input registers into this local variable arguments. We're going to apply the operator lambda to the args and store the result into the output register. Okay, so here it is, it's 0 in this case. We're going to do that for every instruction, and the result of the interpreter is going to be the final last value in this little register array. Okay, so -1 as you would expect in this case. Now, if you look at this interpreter as someone who is a programmer, there is nothing impressive about it, right? It's a little tiny piece of code. And that's the whole point. Like, you can write this interpreter in a very natural way. But while it may not be an impressive interpreter from the point of view of a programmer, it is actually a pretty crazy one from the point of view of something that needs to be passed through a verifier or any kind of a static analysis tool. Just to give you an idea, off of the top of my head, some of the constructs that this thing is using that are extremely hard to reason about statically or dynamically, really, or even as a human being, are, it's doing pattern matching. It's using first-class procedures, high-order procedures. It has side effects. It has a loop, right? These are all of the things that are basically the nightmares of formal methods people. Okay, so I want you to keep that in mind. What Rosette does, it essentially is able to take something like this and generates very simple constraints as output. Okay, so this is what we're going to revisit later. For now, let's continue our example. Okay, so now we're going to see, now that we have an interpreter, how do we implement a verifier for our language? So the verifier for our language, I get to decide, or if you were doing it, you get to decide what the interface looks like at the guest language level. So I chose a very simple interface. So the verify in the guest language takes as input an implementation such as BVMax and a specification, which can be an arbitrary Rosette procedure. So what is an easy way to specify max? Well, just write a conditional, right? So this looks pretty complicated. I don't want to try to write a reference implementation that kind of matches this. So I'm just giving you a specification directly in Rosette. But of course, this can also be a procedure in the guest language. It doesn't matter. This is just for convenience. So the next thing that happens is in order to implement the verify query in the guest language, I will be using the verify query in the host language, and I will do it as follows. The first thing that we're going to do is we are going to introduce some symbolic values into our program. So this construct is going to create two fresh symbolic values of type 32-bit integer, and it's going to bind them to the local variables x and y. As far as Rosette is concerned, as far as you're concerned as a programmer, there's nothing special about these symbolic values. You can actually use them in the same way that you can use concrete values of the same type. Okay, so you can pass them to procedures, you can put them into data structures. There's nothing special about them, right? The only difference really is that Rosette doesn't know their actual value. It only knows their type. The value is determined eventually by the SMT solver once we make a query. So this is what makes the query. So the verify query can take an arbitrary expression, and it will evaluate all paths to this expression. So this is how you should think about it mentally. What's happening, it will execute all paths to this expression, searching for some interpretation that is some binding of concrete values to these symbolic values x and y, such that under that interpretation, under that binding, in that environment, at least one of the assertions in the expression is going to be violated. So in this case, our assertion, we only have one. It's pretty simple. Usually this is much more complicated. It's an arbitrary Rosette expression with generating many assertions actually. And what our assertion is saying is that we are wanting the two programs to be equivalent. Okay, so we want the following to be true. When we interpret BVMax on some arbitrary inputs, the result is always equal to applying our reference procedure specification max to those inputs. Okay, so that's it. We just implemented a verifier. We can, of course, run it. And in this case, otherwise it wouldn't have been interesting an example, there is a bug, right? So it returns a concrete input, 0 and -2, on which the program does the wrong thing. And because we have an interpreter, we can actually see what it does. So if you apply BVMax on these two inputs, we will see that it gives a completely wrong result, right? It gives -1. Now, if I let you stare at this program long enough, maybe until the end of this talk, you would be able to figure out what's wrong, but I will not torture you. So we will actually ask the solver to fix it for us. The way that we're going to do that is by issuing a synthesis query. So I'm not going to walk through this in the same level of detail as the verification query, but I want to show you the code to convince you that is employing the same trick. Okay, I'm going to implement synthesis in my guest language by using the synthesize query in the host language. What you see here is a custom way to define holes in my guest language. Another advantage of Rosette is that it doesn't have any opinions as to what a hole in a program or what an expression in your programming language should be. You actually tell it that. So this little hole that I developed here, this little hole construct, this is about 10 lines of Rosette code. So what this does, it says, I want you to find instructions that are going to fill the registers R2 through R6 with some values using any one of these opcodes in any way they want to. And the synthesizer has to supply, of course, the opcode and the input register and everything. Okay, so the search, if you really think about it, if you do the math, the search space here is huge. Okay, but this is essentially what it's saying. It's saying that I'm expressing a belief that my verification, my original implementation was actually probably almost correct. I believe that there exists a correct implementation that has, just 5 instructions, R2 through R6, and you can actually implement the whole thing just using these opcodes. Okay, so with just this much information, the synthesizer is able to, in fact, complete the program for us and return the correct one. And if you go back and compare this, if you diff it to my original implementation, you'll realize that the thing that I did wrong was I mistyped one of the register names. Okay, so that's it. That's how we build tools in Rosette. You build an interpreter for your language that gives the semantics for your language, and then Rosette takes your interpreter, the program running on top of that interpreter, and some query, and translates all of this to constraints. The key is, or kind of the key difficulty here is that we have all sorts of, and of course, when the solver returns the result, Rosette translates it back up this chain for you into something that's meaningful at the level of your guest language. And of course, the challenge here is how to do this for a real programming language, right? How do we take our interpreter with, which contains all sorts of really difficult to reason about constructs and generate something that's really simple, right? So Rosette reduces everything to the few theories that most SMT solvers are extremely good at supporting. So that's the theory of bit vectors, that's finite precision or machine integers, mathematical integers, mathematical reals, and uninterpreted functions, okay? So how do we go from a full language with loops and recursion and all sorts of things down to something this simple? And I'm going to show you at a high level how that happens. We're going to do it by looking at an example. This example is pretty simple. It takes as input, it's going to be a piece of code that takes as input a list of integers, reverses it, and keeps the positive one. So it's a reverse and filter thing. It's super simple. Here, if we have 3, 1, minus 2, the result should be 1, 3. You would write that in something that looks like Python like this, right? So you initialize this output variable PS to hold the empty list. You iterate over VS. If the value of V is greater than 0, you insert it to the head of the list, and you're done. Okay, so this is super simple. We're going to show you how this works by asking the solver to solve this query. So note that this is, I haven't shown you this query before, but this is dual of verification. So the verifier is demonic. It wants the solver to break the assertions. This query called solve is angelic. Okay, it wants the solver to satisfy the assertions. So what we're saying here is, if I give you some symbolic inputs VS, can you find some binding for those inputs such that this assertion is satisfied? The length of the output list is equal to the length of the input list. So very concretely, suppose that we have these 2 symbolic values, and here I'm using the convention that symbolic values are shown in color. The concrete ones are monochrome. And stare at this as a human being. So it has two values, A and B. And as a human being, what should be the result of this translation? How do you take this loop and translate it so that this assertion is satisfied? What is the essence of this query? What has to be true for this assertion to hold? Now, as a human being, you can tell that the thing that actually needs to be true is that both A has to be greater than 0 and B has to be greater than 0. So this is the best possible translation of this program that we can ever have. Okay, so we just did it manually. Now let's see how we could do something like this automatically, and specifically how people do these reductions, or how they have done them in the past and how they're doing them right now. So both of the methods that I'm going to show you first are very popular, and then I will tell you how Rosette differs from both of these and how it builds on both of these. Okay, so the way that people normally translate programs to constraints, there are 2 of them. One is called symbolic execution, and one is called bounded model checking. Symbolic execution translates the meaning of a program to constraints path by path. So it works like this. You start in a state where VS is bound to these 2 symbolic values, and PS is bound to the empty list. You hit this loop, and V is now bound to A. And when you get to this conditional, you have 2 choices. You have 2 paths you can take. And in fact, you're going to end up taking both of them But let's suppose, for the sake of the example, that we choose to take the then branch first in this case. So if we take the then branch, then we will update the value of the PS to contain the list A. We'll go back to the beginning of the loop. We'll now hit the same decision point again. And for variety, this time we're going to take the else branch. So nothing happens. We just fall through. PS remains the same, and we are done. We hit this assertion, and of course it's false, right? Because the two lengths are not equal. This is 1 and this is 2. We're going to do that for every single path in the program. So conceptually, the result of this translation is the conjunction of all the path formulas that you get through symbolic execution. The advantage of symbolic execution, the thing that makes it so nice, is when you're doing this path by path analysis, path by path translation, lots of things remain concrete. Okay, so even though your program contains lists, there are no lists in your final encoding. Right? It's just a formula over integers. The lists have essentially been stripped away. Okay, so this process of concrete evaluation, sometimes known as partial evaluation, is a really powerful feature of symbolic execution. It allows you to essentially not handle the hard constructs, and that's exactly the point. We want to avoid handling things like loops and lists and so on. Okay, the disadvantage, of course, is that it analyzes every path separately. And in general, the number of paths in a program is exponential in the size of the program. So these formulas can get very, very huge. So that's a disadvantage. We have exponential explosion, even at the encoding level, before you ever get to do any SMT reasoning. So bounded model checking makes a different trade-off. So it actually gets rid of the exponential explosion. And the way that it does it is as follows. So again, we start in a state where VS has bound to AB, PS is bound to the empty list. We hit the conditional, and then we execute both branches. Okay, so the case in which A is greater than 0 and the case in which A is less than or equal to 0. But instead of proceeding separately along the two paths, we're going to merge the resulting symbolic state before proceeding. So once we merge these two states, we get a new symbolic value called PS0, I'm calling it here, which is a symbolic list. Okay, so now this thing evaluates the list containing the value A if A is greater than 0, otherwise it evaluates to the empty list. The problem with this, having this symbolic list, is your complex data type is leaking into your encoding. What that means is the next time around this loop, when you try to do another list insertion, you can no longer do it concretely. You have to encode it into your formula. So either your solver has to reason about lists, which solvers are really good about reasoning only simple data types for the most part, or you somehow have to now encode the meaning of lists and list insertion and so on. So even though the encoding is polynomial, it is much more complex, right? So we have lost this beautiful property that we're only talking about integers. So now we have to think about lists as well. But we have gotten rid of exponential explosion. So the question that Rosette asked was, can we actually have our cake and eat it too, right? Can we have the best of both worlds, the polynomial size encoding that you get with bounded model checking, but concrete or partial evaluation power that you get with symbolic execution? The answer is yes. And we do that by using a new form of state merging. So there is no way to avoid path explosion if you're doing it path by path. You clearly have to do some merging. But how you do the merging is critical, okay? So let me show you how Rosette does the merging. It essentially merges values depending roughly on what class of value it is. Okay, so if it is primitive type that we want the solver to reason about, we actually want it to leak into the encoding, then we merge it in the same way as a bounded model checker. We just generate an ITE node, if then else, which the solver understands, and all of these things that are at the leaves of the ITE node are data types that the solver understands. Okay, so if these two are integers, here's how we merge them to create a new symbolic integer. Nothing surprising there. Now, the interesting thing is what happens if we have two values of a value type. Okay, so some type that is, in PL parlance, not a reference type, okay? An algebraic data type, let's think about it that way, like a list. So if you have two values of such a type that have the same structure, and what it means for two values to have the same structure is, of course, type dependent, but for list, it means they have the same length. You are going to merge them structurally. So you are going to merge them element by element, calling this merge procedure recursively to generate a new list with the same structure. So in this case, a list of length 2 that pushes these ITs into the list. Okay, so I'm just here, I've assumed that C and D and A and B are all primitive types. The recursive procedure did the right thing, and this is the output. Of course, if they were more complex than that, the inside of this list would look different. But the whole point is what comes out is a concrete list. It's not a symbolic encoding of any list. It really is a concrete list of length 2, and you can do things like, look at its first value and so on. Now, the hardest case is the final one, which is what happens when you have two values of incompatible types that are not mergeable either structurally, and they're not primitive, so they're not mergeable in the SMT way. How do you handle them? So if you have a list of length 0 and a list of length 1, well, we do it by introducing a new kind of symbolic value here, and it's called a symbolic union. At a high level, it is just a set of guarded values. Okay, so it's a set of guard value pairs, and when you look at this notation, you can probably guess what it means, and your guess will be correct, right? So it just means the obvious thing. But let me show you why and how this actually helps you do things more efficiently. So we're going to go back to our original example. The first few steps of this symbolic evaluation algorithm are going to be the same as embodied model checking. We're going to execute both branches, and now we're ready to merge. So we look at the situation that we're in. So we have an empty list and a list of size 1. We have no choice. We have to generate a union. Okay, so we generate a symbolic union. And now we are ready to go back to the beginning of this loop and think about what happens when V is bound to B. Now, in the case with B is greater than 0, we would like to insert B to the head of this list. With this symbolic union, we can perform this insertion directly on the members of the union. Okay, so we're just going to push it inside. So again, there is no symbolic reasoning going on. We're just going to execute this insertion directly onto these two elements to get the result. In the else branch, well, nothing interesting happens. We just pass this through. Now comes the hard part. The question is, how do we merge these two states? If you did it naively by taking a union, just straightforward union of these two, you would get into trouble because you would again run into exponential explosion, right? Like every time you do a merge, this doubles. So if you imagine this getting, doing this for something more than list of size 2, list of size n, the result would be in the end something of size 2 to the n. So we're not going to do the naive merge. The way that Rosette's merging algorithm works is as follows. When it has to merge two unions, it respects the following invariant. In the output union, there can be at most one value of every primitive type. Okay, so at most one integer, at most one real, at most one bit vector of size 32, whatever it is. But there could also be at most one value of every possible structure, okay, of a value type. So there can be at most one list of size 0, one list of size 1, at most one list of size 5, and so on. Okay, so in this case, if we did a naive merge, we would have two lists of size 1, but we're not going to do that. We're actually going to merge those two structurally, and we're going to end up with just one of those. Now, if you extend this reasoning for an input list VS of size n, you will notice that the size of this union can never be bigger than the longest path through the program. So the encoding is polynomial in the size of the execution graph that the program makes once you evaluate it, okay? And of course, once we finish this, we have our final merge state. We're ready to hit this assertion. And when we do that, we can evaluate this length concretely on the members of PS, and we can find that the only guard that actually works is this G2, and this is exactly the encoding that we came up with manually at the beginning a few slides ago when we started talking about Rosette. So that's basically how Rosette achieves polynomial-sized encoding and no exponential explosion, essentially through careful merging. So we kind of get the best of both worlds. Of course, none of this is magic. You could write a bad program in Rosette that doesn't scale in the same way that you can write a bad program in Java. There's nothing surprising about that. The only difference is that it's perhaps easier to write a bad program in Rosette. And for that reason, we have a couple of cool tools that actually help you do performance profiling and repair and debugging for your Rosette programs, and to make them faster and to make them scale well enough to handle interesting problems in your domain. So that's it about Rosette. What I'm going to finish with is kind of this brief overview of this Jitterbug application that I mentioned before. And Jitterbug is a tool for verifying JIT compilers, so just-in-time compilers inside of the Linux kernel. So Jitterbug lives on top of a bigger technology stack that we have been developing as part of the UNSAT group at UW, really with the goal of applying verification and synthesis to critical infrastructure software, such as OS kernels. And this is joint work with my colleague Shi Wong. He is the systems part of the FM systems equation that we have going here. And of course, our students, Jacob and Luke, who are the primary authors of the paper. Now, what is Jitterbug? As I said, Jitterbug is a tool for verifying just-in-time compilers in the Linux kernel. So specifically, we are targeting compilers for a language called eBPF, which stands for Extended Berkeley Packet Filter. So let me first tell you what BPF is and why it's really hard to reason about it. So BPF in Linux is essentially a kernel extension mechanism. So if you want the kernel to provide a new service and you don't want to hack the kernel, which is usually a good idea, you as an application submit to the kernel a program written in this language called BPF, and the kernel compiles it to native code and then runs it in kernel mode. So it attaches it to the right subsystem and runs it. Okay? So there are two ways to do this, right? So you could interpret BPF, and there used to be an interpreter for it inside of the kernel, or you could do JIT compilation. It turns out that the JIT is faster. Obviously, that's not surprising to anybody, but it's also more resistant to certain kinds of security attacks like Spectre. So Linux has now gotten rid of the interpreter in the kernel, and it's only using the JIT compilers. Now, because this is so sensitive, right? So you're running native code inside of the kernel that was generated from some code submitted by the programmer, clearly any sort of bug or miscompilation is going to be a serious, not only stability issue, but also security issue, right? So anytime the semantics of the original program differs from the semantics of generated code, it is an opportunity to do really bad things if you're an attacker. And I think some of these things have been exploited before, some of these bugs in the JIT compilers. Okay, so how exactly does the whole process work? How does the kernel submit? How does an application submit a program to the kernel? Well, a BPF is essentially a tiny virtual machine. The language looks a lot like assembly. It has 11 registers, about 100 opcodes, and they cover everything. You can do jumps, of course, arithmetic, and so on. And the particularly tricky thing is that there's also a shared memory. So there is a limited form of concurrency that you have to reason about when you're reasoning about BPF programs, because the shared memory between the BPF program and the rest of the system can be written to by anybody at any time during the execution of the BPF program, okay? So there's, on top of all of this thing, there's also concurrency to think about. So once the application submits the program to the kernel, the first thing that happens is that the kernel runs it through what is called a BPF checker. They actually call it the BPF verifier, but we avoid using the word verifier because that would be just too confusing, too many verifiers going around, okay? So this is the BPF checker. It is a conservative static checker, which makes sure that the code that you submit has no undefined behavior, okay? So no out-of-bound accesses, no division by zero, and so on, and that its execution is bounded, okay? So no non-terminating loops. It just has to finish. Once the program passes the checker, it is passed to the BPF JIT compiler. Now, having this checker is actually really nice because it means that we can state and prove extremely strong properties about these compilers that normally you can't prove about a compiler because, in general, you don't know that the program terminates, but we do. Okay, so the compiler generates machine code directly. It's a one-pass compiler. It scans the BPF program, and for each BPF instruction, it generates a sequence of native instructions. Okay, the code that it generates kind of looks like this. There are three parts. The body of the machine generated machine code implements the semantics of the BPF program, and the prologue and the epilogue are saving and restoring architectural state. So from the point of view of the kernel, this looks just like a regular function call. As you could probably guess from everything I've just said, writing these compilers and reasoning about all of this is extremely hard. There are like lots of moving parts here. So what we did is conduct a study looking at all Linux commits to the BPF compilers in the last 6 years. And we found that there were 82 bugs in these compilers covering every single major architecture. So each of the compilers for the major architectures and every category of instruction. Okay, so to help with this, we developed Jitterbug, which is a system for verifying these JIT compilers. At a very high level, the theorem that we want to prove in Jitterbug is a strong form of bisimulation. So what does that mean? It means that for every source program, every configuration of the JIT and every input data, so for the entire environment, what comes out, this target program is equivalent in the following sense, okay? They produce the same return value and they produce the same trace of externally visible events. Okay, so write to shared memory, they better be the same. So it's a very strong form of bisimulation. Okay, normally you cannot prove this directly with an SMT solver. It's too hard. It's induction, essentially, right? So what we did instead is we proved once and for all. Okay, so for all possible JIT compilers, even the ones that have not been written before, is that if you are able to establish something called stepwise correctness for every single instruction, that there's a translation for every single instruction in your JIT, then the stepwise specification composes it's your reductive invariant, and you know that the JIT is correct. Okay, so we did the induction once at a high level in a parameterized way in Lean. And then the actual nitty-gritty of checking that every instruction is translated correctly by the JIT with respect to the stepwise correctness specification is done by Rosette. Okay, our Jitterbug on top of Rosette. So the way that's done is kind of this architecture. We have the implementation of the JIT, which is written in a subset of C embedded in Rosette. We have the source instruction, which is in BPF, and that's the symbolic instructions, an arbitrary source instruction. The JIT runs on it, and it emits a stream of symbolic target instructions. These things are passed through their individual interpreters in Rosette, fed into the stepwise specifications along with any assumptions and invariants specific to the JIT, and then everything is discharged with an SMT solver. Of course, the important thing here is to write the JIT in a subset of C because we want to be able to extract the code and submit it back to the kernel, which is what we did. Of course, I'm glossing over a lot of details here. You can find them in the paper. There are massive scalability issues that you need to worry about. And even stating the correctness specification is highly non-trivial. So I'll conclude by giving you, by briefly discussing some of the results. We used Jitterbug to develop the first verified JIT from scratch for the Linux kernel. It is for RISC-V 32-bit architecture. We have verified all the existing JITs for every major architecture, in total 5 of them, found a bunch of bugs, fixed them, and we have also submitted a bunch of optimizations because now that we have a verifier, we are confident in writing complex performance optimizations and being sure that they are not impacting correctness. All of these changes have been upstream to the kernel, and that brings me to the end of my talk. Thank you for your attention. I'm happy to take any questions now.
All right, great. Thanks, Emina. That was terrific. I will applaud on behalf of the audience.
Thank you.
So so everybody out there, if you have questions, please post them in Emina's channel on Slack. And I'll just go ahead and get the ball rolling. So I have a couple like low-level questions, but I have one like high-level question. So I feel like, so I want to use Rosette. I have wanted to use Rosette before, but I'm scared.
Oh, the
I'm scared of,
parentheses.
yeah, no. The rocket part doesn't bother me. I was actually, I was a professional Lisp programmer at one point.
Oh,
So
wow.
I'm not scared of parentheses. So my concern is that that there are lots of landmines, and that these landmines would get me in a place where I, as the Rosette programmer, without well, that I would basically be sending you emails, is essentially where I'd be. They're like, help, 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 this doesn't work, this doesn't scale, I did something wrong. I mean, I know about the profiler that you described that James worked on, and that seems like that's helpful for sure to to kind of diagnose these problems and help you find them. But maybe you could, like, are there kind of like broad meta guidelines for like, here's how you should write an interpreter? Like, you might think that an AST interpreter would be a good idea, but, and I actually don't know the answer to this question, like, but is that a good idea or a bad idea in Rosette? What about bytecode based interpreters? What are the pain points? What about, what are the implications of this type driven state merging? Like, it seems, yes, it's, it's polynomial time limited, but, obviously it's collapsing states in some weird way. Are there gotchas there that I need to know about? And then finally, like the big question, like, it's like Rosette, obviously it's a super powerful tool that's enabled a lot of amazing work. But, like your intro is like, hey, verification and synthesis come for free, but this is plainly a lie.
Well, for free compared to what you had to do before. Let's put it that way.
Sure, that's right. Way cheaper.
Way cheaper. Time. Yeah.
Okay, so that's like a ton of questions at once. So I'll let you attack those however you'd like.
Yeah, I mean, those are perfectly legitimate questions, and the answer is, every tool of this kind, the learning curve is steep. There's definitely no doubt about that. But the good thing is that we have a lot of experience now building tools of this kind for really a variety of domains and a variety of languages. Okay, so the thing that I just described in Jitterbug, that is dealing with interpreters of pretty much every kind, right? We have, we have had to deal with decoders for x86 instructions, which is really hard because they're not the same size, for example. So we have had to deal with all of those nitty-gritty details. My advice would be, if you want to try to do something like this, the biggest bang for your buck that you will get is if you identify a series of related problems for which you can build a layer on top of Rosette, and then that layer is going to hide or shield you from some of the gotchas. Okay, so this Jitterbug tool is built on top of this tool called Serval, and we built Serval originally literally for the particular purpose of analyzing system software. And it really knows things like, when you are running a CPU simulator, the thing that you should never let happen, or never let Rosette attempt, because you're going to end up in an infinite loop, just like one of those low-level details, is don't let your program counter become symbolic. That's bad, right? You don't know where to jump and so on. The good thing about Rosette is that it actually gives you low-level control over things like where you split and merge, okay? So it has its opinion about how it should proceed and where to merge states and where to split, but you can actually guide it. Unlike most systems, you can actually tell it, no, you're wrong. You just merged that PC. I don't want it merged. I want you to split into all the concrete parts, execute the paths concretely, behave like a symbolic execution engine, then merge back in and proceed. So there are a lot of those, tricks that we have. There are these layers on top of Rosette that we have built for particular domains. So yeah, my advice would be to really get the biggest bang for your buck. It is best to build a layer on top of it for yourself that is good for your particular purpose. This is not to say that you can't just take it out of the box and build a tool that works. Of course you can, but as you said, there are there are a lot of considerations that exist with any tool of this kind when you try to use it.
Sure, sure. That makes sense. Those are all good points. I like, yeah, I'll have to take a look at the serval paper in more depth. I like the, so I wasn't aware actually that you could control the merging. That seems to be super important. That makes a lot of sense.
Yes. So yeah, without that, I mean, they just wouldn't work. I mean, kind of the fun thing about that the ability to control, so I call it symbolic reflection. It actually enables the program being evaluated symbolically to control its own symbolic evaluation.